Welcome back to a new course. In this video we are going to be talking about deep learning with PyTorch. We are going to be covering the theory of the deep learning, installation of PyTorch, creating tensors, tensor operations, tensor indexing and slicing, automatic differentiation. We are going to create a linear regression using PyTorch from scratch. We are going to talk about modules and layers in PyTorch. We are going to talk about neural network fundamentals. We are going to train a deep learning model, and at the final step we are going to look at how we can save the models that we trained and load them back. I'm going to be adding chapters to this video, so if you want to skip some parts or re-listen some of them, you can check the chapters from the description. Let's start coding. Once again, welcome to the PyTorch course. Before directly start with installation, let's firstly talk about PyTorch, and I'm going to be using Visual Studio Code as my code editor in this course, but you can prefer any code editor that you want. And at the start, I want to create a text file like pytorch.txt, and I want to take some notes. And this is going to be our introduction to PyTorch and what it is. If you want to skip this part and directly jump to the installation and coding part, you can find the chapters in the video bar. So PyTorch is a really popular open source machine learning framework developed by Facebook's AI research lab. So let's type some of them. Open source, and we can say machine learning framework, and developed by Facebook's AI research lab, and I'm going to use a capital letter F right here, and it's widely used for tasks like computer vision, natural language processing, and reinforcement learning. PyTorch allows you to define and train deep learning models in a flexible and easy to use way, so it's really great for research and production. So I'm going to say deep learning, and let's talk about more. PyTorch designed to work just like standard Python code, which means it's intuitive and easy to debug. This will make our life a lot easier, especially when building and testing models. And before this course, I asked ChatGPT to give me the 3 advantages of using PyTorch instead of other machine learning frameworks, and it listed me 3. So I'm firstly going to type the 3 elements, then I'm going to talk about them. So the first one is dynamic computation grabs, and the second one is strong GPU acceleration, and third one is huge community and support. These are the answers from the ChatGPT, and let's talk about them. So at the first part, dynamic computation grabs, PyTorch creates computation grabs dynamically, which means the graph structure can change during runtime. This flexibility is really useful when working with models like recurrent neural networks, where the shape of data can change. And at the second part, strong GPU acceleration, it's easy to switch between CPU and GPU computations in PyTorch with minimal change to the code. And at the third part, we can say about this, like PyTorch has a large active community that constantly creating tutorials, answering questions, and contributing to the library. And I'm actively using PyTorch when I'm working, so it's like a go-to tool for me on deep learning models. Great. Now we can start with the installation. So we are going to install, I'm going to type them right here, PyTorch, Torch Vision, Torch Audio, and I'm not sure if we are going to need anything else, but these are more than enough for starting. So how you are going to install them is you are going to say pip install, and you can directly type PyTorch, Torch Vision, Torch Audio. But if you are using Mac, you need to say pip3. So you can go with pip3, otherwise pip will work. And now, after the installation, when you type this to terminal, we are going to be installing the PyTorch, and after the installation, you can just verify the installation by, let me quickly clear this area by this button. And you can verify the installation like Python, I'm on Mac, so I will say Python 3, C, and I will say import torch, and I will say print torch version. And if you are getting a number from this, like you are getting a version for the PyTorch, just like 200, you are good to go. And you installed PyTorch clearly. So I'm running that, and my answer is going to be 200. So my torch is ready it has the version of 2.0.0 and I can use that right now. Great, so we have PyTorch. Now what I'm going to do is I'm going to just delete this, like we can save it, and I'm going to create something like PyTorch.ipmb. I'm going to be running the course with a Jupyter notebook because I think it's better for courses since we can go cell by cell. And now since we have PyTorch, we can import it easily like this. And I want to show you at the first place that you can check if you have GPU support or not. I'm not going to be talking about setting it up or using it, and I don't have one set up on my machine right now, but how we can check that is you can say torch CUDA is available and it returns a boolean. If you have GPU support, it's going to return true, else it's going to return false, and in my case it's false. And let's say that you have GPUs on your machine. For checking how many GPUs your machine has, you can say torch CUDA device count and you are going to get the response. For example, if you have 2 GPUs set up, you are going to get 2 instead of 0 in here. Now we can start with deep learning. In our first minutes of our course, we are going to be talking about tensors. So let me type that. Like in a markdown, I will say tensor, and let's talk about them. So tensor is essentially a multidimensional array, like a matrix or a list of numbers, but it can represent data of any dimension. And when we say deep learning, we are going to be working with the data types tensors most of the time. So we have different types of tensors and let's start talking about them. So at the first place we have scalars, and this means a single number. So we can also say like zero-dimensional tensor. Next we have vectors, and vectors we can say like it's a list of numbers and it's a one-dimensional tensor. And we have matrices. It is like a table of numbers and it's a two-dimensional tensor. Don't worry, we are going to make examples on tensors too. We are going to talk about creating them, manipulating them, indexing and slicing, and more. And after matrices we have higher dimensional tensors. So we can go beyond two-dimensional with three-dimensional, four-dimensional, and so on, for more complex data like images or video sequences. So we can say like two-dimensional and more. So PyTorch gives us several ways to create tensors, and let's do that. So the simplest way to create a tensor is to pass in a list or array of values. So I will say like data, and I will say 1, and they are going to be floats, 3.0, 4.0, and next I'm going to create a tensor like tensor from list, and I will use torch.tensor and I will pass my data. Now we can check the type of tensor from list, and we can call the tensor from list like this. So here we created a tensor from a simple Python list using torch.tensor method in here. This function automatically detects the type of data you are passing in and converts it into a PyTorch tensor. PyTorch also provides several functions to create tensors with predefined values. So let's create a tensor of zeros. We can call zeros tensor, and we will use torch.zeros like this. And I'm going to call the zeros tensor. We are going to have something like this. And we can call like zeros tensor.number of dimensions, and we are going to see the dimension on this 3 to 3 matrix. So we can create a tensor of ones tensor, and I will call torch.ones this time. And I'm going to call ones tensor. Here we have 2 to 5 matrix, and we can create a tensor with random values. So I will call random tensor, and it's going to be torch.random for 4. So I'm going to call random tensor. We are going to have 4 to 4 matrix in here, and our values are between 0 and 1. So let's discover more methods of creating tensors. Creating tensors are really important because we are mainly going to be working with tensors, so it's nice to have on deep learning to know manipulating them and creating them. So what I'm going to do is I'm going to show you how we can create with range of values. So I will say range tensor, and I will say torch.arrange, and I will call 0 and 10. So we are going to be creating a tensor with a range of values from 0 to 9, like this. Now we can specify a step size on that. So I will say step tensor, and I will say torch.arrange 0, 10, and I'm going to specify the step like 2. So I'm going to call the step tensor in here, and we are going to have this since we specify the step size as 2. Okay, let's discover how we can create tensors from NumPy arrays, because we are going to be doing this a lot since NumPy is a widely used library and we are going to be having data formats on NumPy array type. So I will say import NumPy as np, and I'm going to call something like NumPy array, and I'm going to call NumPy.array. I'm going to give values like this, random completely, 1.5, 2.5, and 3.5. So now I'm going to convert NumPy array to PyTorch tensor, like tensor from NumPy, and I will call torch.tensor. It's just this, and I'm going to pass the NumPy array. So when I call the tensor from NumPy in here, I'm going to have my tensor in here. PyTorch will maintain the data type of the original NumPy array during the conversion. If you need to convert it back to a NumPy array later, you can use that NumPy method. Like I will say tensor from NumPy, and how we can use that feature is we can call torch.numpy, and I will say like this. Actually it says torch has no attribute numpy. I think I just mixed things up. It was like tensor from numpy.numpy. It's going to be like this. Yeah, we have our array back. So this is the correct way. I was remembering wrongly. So I'm going to call the type on that, and we are going to have numpy array in here. So we can go back to numpy arrays like this easily using .numpy method on tensor. So when we are creating tensors, we can specify the data types. Sometimes we need more control over the data types of our tensors. So I'm going to show you the float, integer, and boolean. I will say like float tensor, and it's going to be torch.tensor. I will give values like 1, 2, and 3. And we can specify the data type in here, like torch float 32. And now we are going to have a float tensor, like let me call that. Here it is. So let's create the integer tensor. Integer tensor, and I will say torch.tensor 1, 2, 3, and I'm going to specify the data type like torch integer 32 bits, and I will call integer tensor in here so we can see the data type in here. Let's create a boolean tensor. I will say boolean tensor, and I will use torch.tensor. Next I will say 1, 0, 1. So I'm going to specify the data type like torch.boolean. So now we are going to have our boolean tensor in here, like true, false, and true. Okay, let's talk about tensor shape and dimensions. I already showed you the number of dimensions, but we are going to take a look at both the shape and number of dimensions. So firstly, I'm going to create something like shape tensor, and I will use torch.tensor, and I'm going to create a 3 to 2 tensor real quick, like 1, 2, let's say 3, 4, and we can say 5, 6. Next, I'm going to call my shape tensor. Now we can say like shape tensor dot shape, and with this method we see it's 3 to 2, and we can call like shape tensor dot number of dimensions, and it's going to return 2. It helps us on finding the number of dimensions. Great. Let's talk about tensor initialization using like functions. Sometimes we want to create a new tensor with the same shape as an existing tensor. PyTorch provides like functions for this purpose. So I'm going to create something like base tensor, and I will use torch.once, 2, 3, and I'm going to call base tensor. Now what I'm going to do is zeros like tensor, and I'm going to call torch zeros like, and I'm going to call the base tensor in here. So I'm going to just make it display, and here we can see It created a new tensor with the same shape as base tensor but filled with zeros. We can also do this with random numbers, like I will say random like tensor, and it's going to be torch random like, and I'm going to call the base tensor in here. So when we call random like tensor, we are going to see that we have the same shape tensor, but it's filled with random values. Okay, let's talk about creating an identity matrix. So for that, I will use .I in here. Like identity matrix is going to be torch.I, and I will pass 4. So I'm going to call identity matrix, and we are going to have something like this, where the diagonal is all ones and the off-diagonal elements are 0. It creates a fort for identity matrix. Okay, so let's do another example with tensor filled with specific values. So I will say fill tensor for that, and I'm going to say torch.fill, and I'm going to pass 2, 3, and I will pass 7. So in this case, we are going to create a 2 to 3 tensor where every element is filled with the value 7, just like you see. Great. Now we are going to talk about tensor operations, and let's start with element-wise addition and subtraction. We are going to create two tensors like tensor A. It's going to be torch.tensor, and I will say 1.0, 2.0, 3.0, and it's similar to the mathematical operations. I will say tensor B, torch.tensor, and I'm going to say 4, 5, 6, like this. And now I'm going to do element-wise addition. So for that I will say sum tensor, and it's going to be tensor A plus tensor B. And let's see the result. Sum tensor. So I'm going to call tensor A tensor B. So in this way we are going to see the operation we made clearly. And I'm going to do element-wise subtraction, like tensor B minus tensor A. And let's call the differentiation tensor like tensor like this, and we have 3, 3, 3. So tensors tensor A and tensor B both have 3 elements. Since they are of the same shape, we can add and subtract them element-wise. Tensor A plus tensor B adds each corresponding element from tensor A and tensor B, just like this one. Similarly, tensor B minus tensor A subtracts the elements, just like in mathematics. Now we will do element-wise multiplication and division. So let's say like tensor, and it's going to be tensor A multiplied by tensor B. And I'm going to call that like this. And here we see, let me call the tensor A with tensor B again for seeing them clearly. Here we can see 4 times 1 is 4, 5 times 2 is 10, and 6 times 3 is 18. We can also do element-wise division, like division tensor is going to be tensor B divided by tensor A. And I'm going to call that like this. Here is our results. Like 4 divided by 1 is 1, 5 divided by 2 is 2.5, and 6 divided by 3 is 2. Great. Let's talk about in-place operations. In PyTorch, we can also perform in-place operations, meaning the result of the operation will overwrite the original tensor. Like, let's do in-place addition. I will say tensor A, add, and I will say tensor B like this. Now our result is going to be something like this. So in here we modify the tensor A directly, as you can see. The underscore here after the function, you can see it in here, indicates an in-place operation which modifies original tensor A we have. Also we can do multiplication like this. Let's do that. Tensor A, and I will call multiplication like this. Again, I'm using underscore for doing an in-place operation, and I will say tensor B. Now when I call the tensor A, we are going to see our values are going to be updated. Be careful with these in-place operations as they modify the original tensor, which can lead to unintended consequences if you want to keep the original data. Okay, that's pretty cool. Now let's talk about broadcasting. Broadcasting allows you to perform operations on tensors with different shapes as long as they are compatible. So let's code it. I will say tensor C, and it's going to be torch tensor. I'm going to create a tree tensor, like I will say 1.0, 2.0, 3.0. Next, I'm going to create another tensor with the shape of 3 to 1. Tensor D is going to be torch.tensor. And I will say like 1.0, 2.0 like this in brackets, and 3.0. So now we can create something like broadcast result, and it's going to be tensor C plus tensor D. And let's see our broadcast result. Here it is. Here PyTorch automatically broadcasts the smaller tensor to match the dimensions of the larger one. In this case, tensor C is broadcast across the rows of tensor D, resulting in a 3 to 3 tensor. Great. Now we are going to be talking about a topic that you are going to be hearing a lot when you are working in deep learning area: matrix multiplication and dot product. These are essential for machine learning models. So let's start with matrix multiplication. Let's create two matrices, like I'm going to create a 2 to 3 and 3 to 2 matrices. So matrix A is going to be torch.tensor, and I will say 1 to 3 quickly, and I will say 4, 5, 6. And next I will say matrix B, and it's going to be torch.tensor. I will say 7 and 8, and I will do like 9 and 10, and 11 with 12. So we have this. Now I will say matrix multiplication results, and I will say torch.matrix multiplication. We have this method. I will say matrix A and matrix B. Now our result is going to be in here, just like this. Great. Here with matrix multiplication, we perform matrix multiplication. For matrix multiplication to be valid, the number of columns in the first matrix must match the number of rows in the second matrix. Like we have a 2 to 3 matrix at the first place, and then at the matrix B we have 3 to 2 matrix. So this 3 matches with this 3. Again, the number of columns in the first matrix needs to match with the number of rows in the second matrix. So this multiplication is valid. And the resulting matrix is going to be the row number of the first one and the column number of the second one. So at the result we have a 2 to 2 matrix. Great. Now we are going to talk about the dot product. The dot product is a specific case of matrix multiplication where both inputs are one-dimensional vectors. Like I'm going to create vector A, and I will say torch.tensor. I will say like 1 to 3 quick up. I will say vector B. It's going to be torch tensor, like 4, 5, 6. Now I will call something like dot product, and it's going to be torch dot vector A with vector B. So we are going to have dot product like this. It multiplies corresponding elements and then sums the results, like 4 times 1, 5 times 2, 6 times 3, then 18 plus 10 plus 4. So the result is 32. Now we are going to be talking about a topic that we are going to be using a lot too, which is reshaping tensors. So one of the most common operations in PyTorch is reshaping tensors once again to fit a specific structure, especially when working with data like images or batches of data. So let's create a one-dimensional tensor with 12 elements. I will say tensor E, and it's going to be torch.arrange, and I will call 12. And here we are going to see our tensor E. Here it is. So I will call something like reshape tensor, and I will say tensor E dot view, and I will say 3 and 4 for reshaping the tensor to 3 to 4, like this. Now we have our new tensor in here, and here it is. We can also call the shape on this for seeing the 3 to 4, like this. Great. The view in Torch allows you to reshape a tensor without changing its data. Here, again, we reshape a tensor with 12 elements into a 3 to 4 matrix. So it's important to know that the total number of elements must remain the same when reshaping. Like I said 3 to 4 and it worked, but if I say 3 to 5, it's not going to work. As you can see, it's going to raise an error. Great. Now we are going to talk about flattening a tensor. Sometimes we want to flatten a multidimensional tensor into a one-dimensional tensor. So we can say like we have reshaped tensor in here. Now let's say flattened tensor, and it's going to be reshaped tensor.view, and we are just going to say -1. Now I'm going to call the flattened tensor. Here our shape is one-dimensional. Great. Let's talk about how we can concatenate tensors. So I'm going to create something like tensor G, and it's going to be torch.tensor. I'm going to say 1, 2, and I will say 3, 4. Next up, I will say tensor H, and it's going to be torch.tensor. I will say like 5, 6, and I will say 7, 8. Also, I'm going to add one more bracket to the upper one, just like this. Now we are good to go. Let's call them firstly. Tensor G here, tensor H in here. Great. So now we can concatenate along rows or columns by specifying the dimension column. Like, let's start with row. I will say concatenate rows, and I will say torch.concatenate tensor G with tensor H, and we are going to specify the dimension like 0. Now I'm going to call the concat rows. Here we can see our new tensor. I will call the shape, it's 4 to 2. And I will say concatenate columns, and I will say torch.concatenate tensor G to tensor H, and I'm going to specify the dimension like 1, and I'm going to call the concatenate columns. Here it is. So let's also call the shape on this, and we are going to see 2 to 4 like this. Great. Now we are going to talk about indexing and slicing in tensors. But before that, when I call like tensor A, we have this. So I don't want that. I'm just going to reset the runtime like this, and I will say import torch. Now when I call tensor A, we are not going to have anything like this. So we can continue with creating new ones. We can always overwrite, but I just want to reset the runtime, and now we are good to go. So tensor indexing really important when working with datasets, images and models. Whether we need a single element from a tensor or a subregion of data, PyTorch provides powerful ways to work with tensor sections efficiently. So let's start with indexing. Indexing allows you to retrieve specific elements or range of elements from a tensor, just like you would with a Python list or a NumPy array. So let's start by creating a two-dimensional 3-to-3 tensor, like I will say in here torch.tensor, and I will pass like 1 to 3 at the first place. Next up I will say 4, 5, 6, and I'm going to say 7, 8, 9 like this. Now I'm going to say like, actually it raised an error. Yeah, here we have curly braces. We need brackets in here. Now we are going to be good to go. And I'm missing a parenthesis, a bracket in here. Okay, now we are good to go. I'm going to just check it out quickly. Yeah, great. We have a two-dimensional 3-to-3 matrix in here. Tensor A, number of dimensions, like this. Great. So let's say that we want to access the element in row 1, column 2. So I will say element tensor A, just like in the list or an NumPy array, I will say 1 and 2. So we are going to have the element of 6. Remember, in Python, indices start from 0. So we reached that 6 in here. This is the row 0, this is the row 1, this is the row 2, and this one, 1, 4, 7 is the column 0, 2, 5, 6 column 1, 3, 6, 9 is column 3. So we are reaching to the column 3, row 1 element. Great. Let's take a note in here like tensors are 0 indexed, which means the first index is 0. like the first element is going to be at the index 0. Great. So let's continue. So let's talk about tensor modification. We can directly modify elements of a tensor by assigning new values. Like I will say tensor A again. I will set like tensor A to 1, means that we are going to be modifying the element into row 2 column 1. So row 2 column 1, it's going to be the 8. So let's set this to 99 like this. Now when I call tensor A, we are going to see that we have 99 in here. Great. Now let's move on to slicing. Slicing allows us to retrieve subregions of the tensor based on ranges and indices. So let's do something like first 2 rows and first 2 columns. So let's say like subtensor, and it's going to be tensor A 2 and 2, just like this. So let's call the subtensor. Here it is. We have 1, 2 and 4, 5. This one right over here. Great. Let's talk about slicing a single row or a single column. So let's start with row. Let's say that we want to extract the second row. So I will say second row is going to be tensor A 1 and like this. Now when I call second row, I'm going to see my second row in tensor A, just like this. And now let's extract the third column, which has the index 2. So third column is going to be tensor A. I will say 2 like this. And when we call the third column, we are going to see that we have this over here. 3, 6 and 9. Great. So let's talk about slicing with step size. So I'm going to call like tensor A again, and I will say step rows is going to be tensor A, and I'm going to say like 2, this is going to be the step, and I'm going to call the step rows in here. Here it is. It take 1, 2, 3 and 7, 9, 9, 9, since our step size is 2. This selects every other row, and for the column side we can do like step columns, and I'm going to say tensor A 2 like this time, and I'm going to call step columns. Here we have 1, 4, 7 in here and 3, 6, 9. Great. Now we are going to talk about Boolean masking. So we are going to create a mask where elements greater than 5 are going to be true. So I will say mask, and it's going to be like, let's also correct this one. We are missing an S in here. Mask is going to be tensor A greater than 5. So I'm going to call the mask in here. We have the booleans, and I'm going to use the mask to extract elements greater than 5 using like mask tensor. It's going to be tensor A, and I will pass the mask in here. So when I call the mask tensor, we are going to have this. We can also modify the tensor elements using boolean masks. Like let's set all elements greater than 5 to 0. But firstly, I'm going to call the tensor A for you to see. Now I will say tensor A, and I will say tensor A greater than 5 is going to be 0 like this. Now I'm going to call tensor A, and here we have zeros in the values where they are greater than 5. Great. Let's talk about indexing with integer arrays. So I'm going to create something like tensor B, and it's going to be torch.tensor, and I will say like 10, 20, 30, 40, 50. I'm going to have a one-dimensional tensor in here, and I'm going to use an integer array to select specific elements. So I will say indices, and I will use torch.tensor, and I'm going to say like 0, 2, 4, and now I'm going to call the indices in here. I'm going to filter that using selected elements is going to be tensor B indices. Now at the selected elements we are going to have this one. In here elements at position 0, 2 and 4 is selected. We can also use integer arrays to index multidimensional tensors. Like I'm going to create a two-dimensional tensor in here, like tensor C, and I'm going to say torch.tensor, and let's create something like 10, 20, 30. Next I'm going to create something like 40, 50, 60, and let's say 70, 80, 90, and the dimension in here is going to be 2, like this, and I'm going to call tensor C. Now I'm going to say like row indices, and I will say it's going to be equal to the torch.tensor, and I will say 0, 1, 2, like this. Next I'm going to say column indices, and it's going to be torch tensor 2, 1, 0, like this. Now let's say like selected elements, two-dimensional, it's going to be tensor C row indices with column indices, and I'm going to call the selected elements two-dimensional right now. Here is our result. We picked the 30, 50 and 70. Great. Okay, that's enough for the tensor basics. Now we are going to talk about automatic differentiation with AutoGrad. So let's type it like automatic differentiation. Okay, so what I'm going to do at the first place is I'm going to be talking about it a little bit, and then I'm going to show you how we can code it. So we are going to be focusing on the AutoGrad module of the PyTorch, which automates the process of calculating gradients. Gradients are crucial for updating model parameters during training, so understanding how to compute and use them is essential. In PyTorch, every tensor has a flag requires_grad. If requires_grad equals to true, PyTorch will track all operations on the tensor and automatically compute gradients during backpropagation. So what I'm going to do is I'm going to create something like x, and I will say torch.tensor, and I'm going to say 2 and 3, and I'm going to set the requires_grad as true. So let's print the tensor x like this, and see that we have the requires_grad true in here. Let's perform some simple operations with a tensor that has requires_grad true. PyTorch will create a computation graph to track these operations. Like, let's do some operations. Y equals to x multiplied by 3, z equals to y dot sum. Now we are going to have the y and z like this. So you can see that we have the grad function in here, multiplication backward and sum backward in here. This too shows that PyTorch is tracking these operations and compute gradients if needed. Now let's compute the gradients using backward. I will say z backward like this, and I'm going to call like x.gradient. Actually, we are not going to use parentheses on there. Now we are going to see we have the 3, 3. So why we have 3 in here? Since z equals to x first multiplied by 3 and x1 multiplied by 3, the gradient of z with respect to each element of x is 3. Since the derivative of 3x with respect to x is 3, we got the 3's in here in this side. Gradients also work really good with multidimensional tensors. So let's talk about them. A is going to be, let's create a two-dimensional tensor like torch.tensor, and I'm going to say 2, 0, 3, 0. Next I'm going to say 4.0, 5.0, and I'm going to set the requires_grad as true. Now I'm going to call the A in here. Here we have this. Now I'm going to perform some operations like A, let's say B is going to be equal to the A element-wise square, and let's print B. Now I'm going to say C is going to be dot mean, and let's see our result on the C. Here we have the tensor of 13.5. Now I will see C dot backward, and I'm going to say A dot gradient like this. Now we are going to see that we have 1, 1.5, 2 and 2.5. So let's see the A2 in here, 2, 3, 4, 5. So why these values? Since C is the mean of A squared like this, the gradient computed as 2A multiplied by 4, where 4 is the total number of elements. Sometimes we don't want to PyTorch to track gradients. For instance, during inference, which means testing, where we don't need gradients to be calculated. So we can use torch.noGradients. Let me show you quickly. With torch.noGradients, which disables the gradient tracking, y equals to x multiplied by 2. And I will say like print y without gradient tracking, and I'm going to print the y in here. So this temporarily disables gradient tracking, which can improve performance during inference. We can see that at the y side we no longer have grad function, meaning PyTorch isn't tracking operations for automatic differentiation. If you don't want to get a version of a tensor that doesn't track gradients but still perform operations on it, you can use .detect method. Like xDetect is going to be x.detect, and I'm going to call x with this. X is in here. Now we have the recursive gradient in here. I'm going to call the xDetect. We are going to see that we don't have recursive grad true in here. Let's perform operations on the detect tensor and see if we are going to have recursive grad or not. We are not going to have, like y_detect is going to be xDetect multiplied by 2, and I'm going to print the y_detect. Here you can see that we don't have recursive grad true. By default, gradients are accumulated in tensors, meaning that after calling backward, the gradients are added to any existing gradients. This is useful during training, where gradients need to accumulate over multiple mini batches, but we can also reset them manually. Like I will say x gradient 0. This is going to reset the gradients of x to 0, like this. Actually, I need an underscore after 0, like this. Now it's going to work smoothly. Now let's perform another operation and backward pass. I will say z is going to be equal to the x square, like this. I will say sum, and I'm going to just display the x in here, and I'm going to display the z in here. Now what I'm going to do is I will say z.backward. And when we do that, we are going to see that at the x.grad side, we are going to have 4 and 6. So why we have 4 and 6? I'm trying to explain everything, but I'm not going to do this for all of them, but I'm also trying to follow with the mathematics on the course. So z is going to be equal to the x0 squared x1 squared. So in here, the gradient is going to be 2 multiplied by x, which gives us 4 and 6 for x, 2 and 3, like this. Okay, let's talk about higher order gradients. PyTorch can also compute higher order gradients, which is useful for certain optimization techniques. So let's create a tensor. X is going to be torch.tensor. I will say 2, 0, and I will say recursive grad true. Now let's display the x in here. What I'm going to do is I'm going to say like x and third power like this. I'm going to call the y. Here we have the 8. So I'm going to say for the first backward pass, which means the first derivative, I will say y.backward, and I will say grad true. Now when I call the x.grad, we are going to see that we are going to have 12. So now we are going to build a linear regression model from scratch in PyTorch. So it's going to help us to understand how model learns from data. So let's say like linear regression model from scratch. And at the first place, let's talk about linear regression firstly. So linear regression is a simple model that predicts a continuous value based on a linear relationship between input features and the target variable. So we are going to, let's think like we have 2 columns in a data set, education and income. So we have the education years in here, and we expect to income to increase when education increases. Like I will say 20,000 in here, I will say 30,000 in here. And based on this data, when we see education year 5, we predict income is going to be 15. So we are going to have an idea, since we have this background information, and when a value comes like this, we can predict its target feature. So mathematically, we are going to have y predicted equals to x plus b. So in here, y prediction is going to be the predicted value, w in here is the weight, x is going to be the input feature, like education according to our example, and b is going to be the bias, which also is going to be intercept. So when x is going to be 0, this is going to be the intercept on the y-axis. So let's start by creating some data for training. I'm going to be creating the data in the video. I'm not going to use any external data sources for you to follow the codes. Let's say like firstly number of samples, it's going to be 100. We are going to have 100 data points, and I'm going to set the x like torch.random number of samples, and I will say 1. 1 means in here is one feature. So we are going to build a basic model. X, we have something like this. I'm going to delete it real quick. Now I'm going to say something like true weight 20, true intercept 50, and we are going to say y is going to be true weight multiplied by x plus true b, and I'm going to create some noise like torch random number of samples multiplied by 0.5. So this is going to be our noise in here. I'm going to call the y for you to see. Here we have the data points in here. So I'm going to be deleting that. And now we generated 100 random samples for x from a normal distribution. Our target y has the equation like 2x plus 5 with some noise added in here for making our data a little bit more realistic. Now we are going to initialize the model parameters. Like I'm going to say weight is going to be torch random 1 because grad. We are going to set this as true. And for the intercept I will say torch random 1 because grad true. So I'm going to call the bias. So our true weight in here is 2. Now we created a random value like 0.88, and our true intercept value is 5. Now we have 0.7. So we are going to be training a model for making this W and B to learn from the data and become similar to these points like 2 and 5, the true values. Now we have random numbers. With training, we are going to be setting them up, like we are going to be changing them, and we are going to be teaching them how our data can be modeled. So we are going to define the forward pass of the linear regression model. This function will compute the predicted values of y predicted using the equation y equals to weight multiplied by input plus intercept. So we will say define linear model, and we will pass x inside. We will say return weight multiplied by input plus intercept. And next I'm going to say like let's test it. Our model, linear model, we are going to pass like the first 5 samples of the x like this, and let's see our y predicted. Great, it's working smoothly. So our function computes the predicted output y predicted when the given input x is provided, just like we wanted. Now we are going to define the loss function. In order to measure how well our model is performing, we need to compute the error between the predicted values y predicted and the actual targeted values y. So a common choice for a regression problem is mean squared error, so we are going to be using that. I will say define mean squared error loss, and we are going to be passing the predicted value from model and the true values. And after that we are going to be calculating it like return y predicted. Actually, I will say return y predicted, and we will say minus y true. We are going to take the second power, and we will say mean like this. This is going to be our loss function, and just for testing it, let's test our loss value with the predictions we made for example. So we will say initial loss, and it's going to be mean squared error loss with y predicted and y the first 5 samples. So these are the true values and these are the predicted values from model, and we are going to say like initial loss dot item, and we are going to have the mean squared error value of 15.24. Now we will define the optimization step using gradient descent. This involves calculating the gradients of the loss with respect to weight and the intercept, and then updating these parameters in the direction that reduces the loss. So it's the important step. I will say learning rate. I'm going to use 0.01, and I'm going to define gradient descent like this. We have functions for making this operation automatically in PyTorch, but I'm going to code it from scratch since it's going to be easier for you to understand the logic behind that. So at the first place, we are going to be computing the loss for the entire dataset. I will say y prediction, and I will say linear model x. And at the loss side, we are going to say mean squared error loss, y predicted, and y. So next up, what we are going to do is we are going to do backpropagation to compute gradients of weight and the b. So I will say loss dot backward. And next up, what I'm going to do is, by the way, I'm going to call the b as bias from now on. If I say bias, you can understand it's b. So now we are going to update the parameters using gradient descent. I will say with torch, no gradients, like this. By the way, in here, again, we are temporarily disabling the gradient tracking for the updates. I will say weight minus equals to learning rate multiplied by weight gradient. And next, I will say bias minus equals to learning rate multiplied by bias gradient. And I'm going to reset the gradients to 0 after the update, like w gradient 0 like this, and I will say bias gradient 0 like this. Now we are going to return the loss item like this. We are going to be returning this, just like this one. And next, what we are going to do is we are going to say, by the way, return is not going to be inside the width, so like this. Here is our gradient descent is ready. So I'm going to say, like, let's perform a single gradient descent step. Loss value is going to be gradient descent function we defined. And we can, actually we have a problem, let's quickly fix that. So at the right side we have torch. Actually it seems okay. Let's continue. We have the linear model. Okay, it seems okay. Now I'm going to continue, like, this seems okay to me. I'm just going to make a quick change in here. I will say global, weight, and bias. So let's see if it's going to make change on anything. Yeah, now we can see the loss after one step, like I will say loss value. Here it is. So our goal in the training loop is minimize this cost as much as possible. So again, in the gradient descent function here, we calculate the current prediction and loss. We call backward to compute gradients of weight and bias. Then we manually update weight and bias by subtracting the learning rate multiplied by the gradients in here. Finally, we reset the gradients to 0 before the next update. Now, in the next step, we are going to extend this to multiple iterations. We will run the gradient descent optimization for several epochs to minimize the loss. So I will say number of epochs, and it's going to be 1000. Let's say, like, for epoch in the range number of epochs, loss value is going to be gradient descent like this. Next, I will say, actually, I'm going to fix the typing in here. Next, we are going to print the loss in every 100 epochs. So if epoch plus 1, 100 equals to 0, print epoch, and we will say epoch plus 1, and we will say loss value, and we can make it look pretty like this. And next up, I'm going to say, like, in here, I'm just going to make this run, and here we see that our loss gets lower with training, and I will say I'm going to print the trained weight and trained bias. So trained weight is going to be 2 this time. Trained bias is going to be 4.96. So remember, I'm going to go to the true values in here. Our true weight is 2 and true bias is 5. So we get similar values to that right now. It was like random numbers. Let me quickly check if I can find that. It was like 0.8 for both weight and bias. And now it's 2 and 5 since we trained these values. After training, the model learns weights and bias values, which are close to true values once again. So let's visualize this. I will say import matplotlib.pyplot as plt, and I will say plt.scatter x.numpy, and I will say y.numpy, and I'm going to set a label like data points, and next I'm going to say color blue alpha 0.5. Next I'm going to say plt.plot like this x.numpy linear model. I'm going to passing the x, I will say detect, then I will say numpy like this with dot of course. Now I'm going to say label is going to be fitted line, and let's set the color as red. Next up, what I'm going to do is I will say plt.label x. We are going to change this to x label, plt.ylabel, it's going to be y, and we will say plt.title linear regression with PyTorch, and we can set the legend on, and I will say plt.show. So we are going to have a line like this. We trained this linear regression model from scratch in here. Seems pretty good and seems like it fitted to the data really well. Great. Now we are going to talk about the modules and layers. So let's type it out. Okay, let's talk about it. In PyTorch, a module is the base class for all neural network components. It encapsulates parameters, buffers, and methods for forward propagation. A layer is a specific type of module that represents a single transformation in the network, like a linear transformation or a nonlinear activation function. So let's start coding. I will say import torch.neural network as neural network. Next up, what we are going to do is, also we can import torch too. We already imported that, but we are going to import them both like this, and we imported torch.neural network for neural network modules. Now, let's create a simple neural network class by inheriting from neural network module. This will allow us to define our layers and the forward pass. We are going to talk about the neural network components like activation functions and stuff in the upcoming minutes, but for now I'm going to be using them, but we are going to explain them later on the course. So I will say class simple feed forward neural network, and now in here I will say neural network dot module like this. Next up I will say define. I'm going to say self. We are going to give input size. We are going to give hidden size. We are going to give output size, and then we are going to say, actually we need a space in here, then we are going to say like super simple feed forward neural network and self like this. And next up, actually I'm going to use like this, initialize like this. Next, now we can define the layers. Like in here I will say self fc1 neural network.linear input size and hidden size. Next up I will say self.ReLU and rectified linear unit like this, and after the activation function I will say like 2 linear 1 hidden size and the output size. So I'm going to define the forward pass like forward self x. I will say in here out Next, I will say the linear transformation. Now we are going to be talking about activation in here. And next, at the end, we will say self to out. And we are going to be returning this out at the end. So we are going to be taking a look at them differently on the init and the forward side. In the init side, here we have a fully connected layer transforming inputs of size, input size to hidden size. Then we have an activation function for introducing nonlinearity. And then we have another fully connected layer transforming from hidden size to output size. And in here with the forward method, it defines how data flows through the network. We first pass x through the first layer in here, then we apply the value activation and then pass it through the second layer and we return them at the end. So this is like the structure for the modules and layers. Now we are going to talk about the neural network fundamentals. Like I'm going to say neural network fundamentals. And we are going to learn about activation functions and stuff in here. After learning about the fundamentals, we are also going to train a neural network model using the things that we are going to learn right now. So, a neural network is a computational model inspired by the way biological neural networks in the human brain operate. It consists of interconnected nodes organized in layers, an input layer, one or more hidden layers, and an output layer. So I'm going to type them like input layer, hidden layers, and output layer. So one by one, input layer. This receives the input data, the features we have. In our regression example, it is the education. Hidden layers. This perform computations and feature extraction. There can be multiple hidden layers, making the network deep. Output layer. This produces the final output, predictions or classifications. And let's create a simple like structure of neural network. We are going to have input layer, let's say like x1. I'm going to make them like this, x2, x3 to xn. And we are going to have like hidden layer. Also we are going to have output layer. And now I'm going to say like an arrow in here. Also we are going to have weights and biases. So this is a pretty simple example. I will say hidden layer 1, hidden layer 2, and hidden layer 3 to again hidden layer n. I'm going to type it like this. And next up we are going to have weight 2, bias 2 like this. And at the output layer side we are going to have, let's think of a binary classification problem. We are going to have y1 and y2. So each neuron in a layer receives input from the previous layer, processes it using weights and biases, and passes it through an activation function before sending the output to the next layer in here. Each connection between neurons has an associated weight, and each neuron has a bias. Okay, let's keep talking about the neural network topics. So I'm going to be talking about activation functions right now. Activation functions introduce nonlinearity into model, allowing neural networks to learn complex patterns. Without activation functions, a neural network would behave like a linear model regardless of how many layers it had. So let's talk about the common ones. I'm going to start with sigmoid. So I will type sigmoid and let's talk about it. Sigmoid has the output range between 0 and 1, and its formula is the input feature in here 1 divided by 1 plus e to the power of minus x, and it is used in binary classification tasks, which means if we have a target with the features only 0 and 1, the binary classification problem, then we can use sigmoid. And next up we have the 10H. So it has the output range of -1 and 1. And next, at the formula side, we are going to say x is going to be equal to the e power of x minus e power of minus x divided by e power of x plus e power of minus x. And it's used in hidden layers. Next, we have rectified linear unit. So I'm going to type it too. It has the output range limitless from 0. Like, its output ranges from 0 to endlessly. So how can I write that? I don't know the keyboard combination to do that. Let me try one. Oh yeah, that worked. So it has the limit of 0 at the left side, and at the right side we have no limits. And actually I don't know why it's red. Yeah, okay, now cool. Next up, we are going to say for its formula is going to be like value x, maximum of 0 and x. And it's used because it's simple and effective. Also, we are not going to leave space in here since we didn't use that in others. And at the last place we have softmax. So I will say like softmax like this. This converts logits to probabilities for multi-class classification. And the formula of this is softmax xi is going to be e to the power of xi divided by sum e power xj, like this. So let me check what we use in the last example. We used ReLU, so let's make a quick example with ReLU. So we are going to say import torch neural network functional as f. Then I will say like sample tensor. I'm going to create a tensor with both negative and positive values. Like I will say -1, 0, 0, 1, 2. So I'm going to pass them into ReLU, and we expect it to set this negative value to 0 and keep the positive ones unchanged, since we see the output range, it's 0 to endless in positive direction. So ReLU output is going to be ReLU, and I will pass the sample tensor. So we are going to see 0, 0, 1, 2, just like this. Yeah. Now we are going to talk about the loss functions. I'm not going to type their formulas since it can be long, but I'm going to talk about what they are. I'm only going to talk about the common ones. So at the regression side, we have the mean squared error, and we can type to this like used for regression tasks. And we have binary cross entropy, which is used for binary like this, used for binary classification tasks. And we have categorical cross entropy. As you can expect, it's for multi-class classification tasks. Like I can type used for multi-class classification tasks. And we already used mean squared error in simple linear regression implementation, but you can use f.mean squared error loss like this. Remember, we imported neural network functional as f for using mean squared error. Also, let's use it. So I'm not going to import this again, and I'm going to create two tensors like for showing the mean squared error loss. I will say y true, and it's going to be equal to torch.tensor. I will say 3, 0, 0, 0.5, 2.0, and 7.0 like this. And it's a markdown object, so I will do that in here. Next I will say y predictions torch.tensor. I will say 2.5, 0.0, 2.0, 8.0. Next I will say loss is going to be equal to the f mean squared error loss, y prediction, and y true. So we are going to get our loss like this. Okay, let's talk about the optimization techniques. Optimization techniques are used to adjust the weights and biases of the neural network to minimize the loss function. Remember that we updated our linear regression parameters in the way that we minimize the loss function. The most common optimization algorithm is stochastic gradient descent, like this. Stochastic gradient descent. This updates weights using the gradients computed during backpropagation. And let's talk about the training process. So at the training process, we generally have several steps like forward pass, compute loss, backward pass, and update parameters. Let's talk about them. So at the forward pass side, we compute predictions using the current model parameters. Then at the compute loss side, we measure how well the predictions match the target values. At the backward pass side, we calculate gradients using backpropagation. And at the update parameters side, we adjust the weights and biases using optimizer. So it's going to be looking something like this. For epoch, in range number of epochs, at the first place forward pass, we will say output is going to be model input data like this. Like we didn't define anything, but I'm just showing for explaining the logic. We are going to calculate the loss, like loss function, anything mean squared error, cross entropy loss, output and target. Then we are going to do the backward pass and optimization, like optimizer, zero gradient. Next we will say loss.backward, and we will say optimizer.step, like this. So this is going to be a training loop. Now we are going to train a neural network. We are going to cover the entire process in this part of the course. So we can directly start. I want to work on a regression task, so I'm going to create a data for that. Like I will say number of samples, let's use 1000 this time, like this. And for the x side I will say torch random number of samples 1 multiplied by 10, and this means random input values between 0 and 10. By the way, I'm going to type that in a Python cell like this. Also in Jupyter Notebook you can change by clicking in here. Like if you click on markdown in here, you can select Python, but both ways are okay. And then I will say y equals to 2 times x plus 1 plus torch random number of samples and 1. Like again, this is going to be our noise, just like in the linear regression example we have. I will say x and y for showing you what we have. Great, we have our tensors ready right now. And we have the formula of y equals to 2x plus 1 with noise. Now we are going to define the model. Again, I'm going to do the import. Since this is a different section, like torch.neural network, I will say as nn, and we are going to use a simple feed-forward neural network for regression. So I'm going to say class simple feed-forward neural network, and I will say neural network.module. Actually, we can use the same one. Let me copy that. It was in here. Let's take this one and paste it in here like this. So here's the input layer, and here's the activation function, and here is the hidden layer. Great. This is the from input to hidden, and this is the from hidden to output. And now I'm going to instantiate the model. Like model is going to be simple feed forward neural network. So I'm just going to say restart to the runtime, and I will just save this. I'm going to import the torch too, and I'm going to say this. Now I'm going to make this run, I'm going to resave this. Here I'm going to make some change to our old code, like in here I'm just going to delete these three: input size, hidden size, output size. I'm going to define them manually, like I will say 1, 10, and then I'm going to set 10 to 1 in here. So this means that we create a neural network with one hidden layer in here containing 10 neurons, and the value in here introduce nonlinearity. So I'm going to make this run again. I'm just going to type the layers like this, and I'm going to reinstantiate the model. And next up, what I'm going to do is I'm going to define a loss function and optimizer. I will keep all the steps simple since we are training a neural network for the first time. That's why I define numbers like this, and I'm going to be using functions from the neural network module and torch for the optimizer and loss function steps. So loss function is going to be neural network mean squared error loss, and optimizer is going to be torch.optimizer stochastic gradient descent like this. I'm going to pass the model.parameters inside in here like this. Like, let me show you what this returns. So we have a problem like this. I guess we forget to add parentheses on the instantiation part. Now it's going to be working smoothly in my opinion. Like model.parameters are working smoothly, and we are going to define our optimizer right now. Like I will say learning rate is going to be, like, let's say 0.01. So it's going to be ready to use. We have our loss function here, mean squared error loss, and we have our optimizer ready to update the model parameters. Great. Now it's time for setting the training loop. Since this course is a little bit long, I'm trying my best to not do any type of typing errors, but sometimes I make some mistakes, so just like in the parentheses side on here, so forgive me on that side. I will say number of epochs, let's set this to the 1000. And next I will say for epoch in range number of epochs, we will say model.train. This sets the model to the training mode, and then we will say output is going to be model x. This is the forward pass, and we are going to compute the loss, like loss function, output and y. And next what we are going to do is we will say optimizer 0 gradient. We zero the gradients from the previous iteration, and we will say backward pass loss.backward. And next up we are going to say optimizer.step, which means updating the parameters. And next up what we are going to say is we are going to print the process, like print if epoch plus 1. Let's print for every 50 epoch, like 50 equals 0, then print epoch, and we are going to say epoch plus 1 divided by number of epochs, and we will say after that loss is going to be in here loss.item and for float like this. Now I think we are ready to go, and I'm going to make this run like this. Before the results, let's talk about it. In here we set the model to the training mode, and then we perform forward pass, and we calculate the loss using the true target values y. Then we reset the gradients. In here we compute gradients with loss.backward. We update the model parameters using optimizer.step, and we print those using this line. And here we see that we start with a loss value of 30, and at the end we have the 2.7. So we lowered our loss, which means that we trained our model successfully. And we can plot the training loss. Like we can say import matplotlib.pyplot as plt, and we need to define a list in here like losses. I will say losses, and it's going to be an empty list for now. And in here I'm going to say like losses.append. I will add the loss.item like this, and I'm going to make this run. So also I need to make this run firstly and create my empty list. Now I'm going to make this run. It keeps training from the previous point, but it's not important. Next up, we are going to have our list in losses like this. Here is our list for the loss values, and I'm going to say like it's the second training, by the way. Again, I will say plt.plot range in number of epochs losses, and I will say like label is going to be training loss, and I will say x label is going to be epochs, y label is going to be loss, and title is going to be training loss over epochs. And I will use plt.legend, and I will use plt.show. So we are going to have something like this. Now for the final step of this course, I'm going to show you how you can save your trained model. Like we are going to say torch.save, and we will say model.state dictionary in here, and we need to specify the name like simple feed forward neural network.path like this. So we are going to have our model file in here, and when we want to use this model for predictions or other things, we don't need to retrain it. Like we trained our model for 2 times, and if we want to use that model, we don't need any type of training from now on. We just have that in here. This .save and .state dictionary commands saves the model state dictionary, which contains all the learned parameters, weights and biases. And if we want to load it back, what we can do is we can simply say like we need to define the same model class like at the training phase. I'm just going to copy that and create this with a different name like this, and I'm going to say like loaded model. And now what I'm going to do is I will say loaded model is going to be loaded model, and actually we need to change the name in here too. Now it's going to work smoothly. Yes. Now I will say loaded model that load state dictionary like this. I will use torch.load in here like this, and I'm going to give the name in here. So I'm just going to copy this in here. I will say copy, I will paste this in here, and now we are going to have the output of all keys matched successfully, which means that we successfully uploaded our weights and biases, and we are ready to use our model. And we can just set this to evaluation mode like loaded model.evaluation. And for the final step, I'm going to talk about the difference between the training mode and evaluation mode. When a model is in training mode, it enables certain behaviors that are necessary for training like dropout and batch normalization. So at the dropout side, this is a regularization technique where randomly selected neurons are ignored during training. This helps prevent overfitting by making the network robust. And at the batch normalization side, this updates the running statistics used for normalization during training. And in the evaluation mode, we disable the training specific features like this, and we are going to be ready for predictions. Using the appropriate mode is critical because it ensures that the model's predictions are based on its full capability and correct statistical properties. If you don't switch to evaluation mode, the predictions may be less reliable, particularly for models that use dropout or batch normalization. And if you want to make predictions after this evaluation mode set, you can just do like loaded model, and you can pass a tensor inside this. Like example, we can say torch.tensor, and we are going to set something like 2.0 like this. And I'm going to pass loaded model like Example. Now here we see a result from our model. And we covered a lot in this course. I hope you liked it. I will be really happy if you can drop a like, and I'm going to be reading all of the comments. If you want to share your thoughts about this course, I will be more than happy to read it and reply. Let's summarize what we did in this course and then we can finish this tutorial. So in here we started by talking about the installation of PyTorch, and then we talked about tensors and tensor operations, tensor indexing and slicing. Next up, I'm trying to find the other sections. We talked about tensors, masking, and we see that we talked about automatic differentiation. And next up, I'm checking my notebook. We create a linear regression model from scratch in this course. Like, we defined everything by ourselves, and here is the visualization of the line we fitted. We talked about the modules and layers, and we talked about the neural network fundamentals in here, like the structure, activation functions in here, loss functions, the training steps, and we trained the neural network by ourselves. And at the end, we learned about how we can do model saving and loading back in our apps, and we learned how we can make predictions with the model we trained. Great, let's get to the outro. Thanks for watching this Deep Learning with PyTorch course. I have a playlist named Data Science Full Courses and Projects where I have more than 40 videos. Just like this one, I have courses and data science projects on there. You can reach to that YouTube playlist from the cards of this video or from the links in the description. I'm also sharing a new data science video every week on my channel. You can subscribe to my channel for more videos like this. Have a great day.